Hi, I'm Randy Appel, and I'm your Regents tutor. And in this lesson, you're going to learn everything you need to know about redox and electrochemistry. Now, the first thing you need to understand is what a redox reaction is. And that will kind of help you figure out everything you need to know later on. And one of the really important things about this unit is everything I teach you is going to carry over to the next part of the lesson. So it's really important that you listen to what I'm saying. If you need to pause, if you need to stop and rewind to hear what I'm saying again, then do it for this lesson, because this lesson is really cumulative and it follows through. A redox reaction involves a transfer of electrons. Transfer of electrons. Now, let's say we take sodium and chlorine and we want to make sodium chloride. Well, remember from bonding, and you can refer back to the bonding concept to learn more about this, but you take sodium and chlorine. Sodium loses an electron, chlorine gains an electron. There's a transfer of electrons to form sodium chloride. Because sodium lost electrons, chlorine gained electrons. That's a redox reaction, because one of the species, and we call it species in chemistry, one of the species lost electrons and the other species gained the electrons. So any redox reaction shows a transfer of electrons. Now, you need to understand the following term, mnemonic device, that I'm going to teach you. And it may sound a little weird, but it will help you understand oxidation and reduction, which represents the loss and gain of electrons. What's the sound a lion makes? A lion, yes. Grr, right? Lions go grr. Well, there's a lion called Leo. If you remember that Leo, the lion, goes grr, you will never forget oxidation and reduction. Leo, lose electrons, oxidation. Grr, gain electrons, reduction. If you remember Leo the lion goes grr, or just Leo goes grr, you will never forget what oxidation and reduction are. And you need to know what oxidation and reduction are. So I'm going to say it again. Oxidation is losing electrons. Reduction is gaining electrons. And remember, you're dealing with electrons. So when you lose electrons, you actually increase the charge, or the oxidation number, which we'll talk about. When you gain electrons, you get more negative, because their electrons are negative. Now, what is oxidation number? Oxidation number shows how many electrons are gained or lost. Now, on the periodic table, they show selected oxidation states. And it doesn't matter if you can see them right now. You go to your periodic table, you see on the top right-hand corner, selected oxidation states. That's what that atom does in a reaction, when it's either gaining or losing electrons. And that's what the oxidation number shows. When you lose electrons, your oxidation number increases. So in oxidation, your oxidation number increases. When you gain electrons, your oxidation number goes down. That's actually why it's called reduction. People say, why is it called reduction if you're gaining electrons? Well, the reason it's called reduction is because the oxidation number gets reduced or goes down. It's oxidation reduction. You need to understand the rules for assigning oxidation number. And these are all listed carefully on your Regents Tutor review sheet. But I'm going to go through them relatively quickly, but you just need to memorize these. The first rule deals with substances that are alone, free elements, elements that are uncombined. Anytime an element is uncombined, its oxidation number is 0. So let's say we have sodium. Let's say we have the first reaction we talked about. Sodium plus chlorine gives you sodium chloride. This Na has an oxidation number of 0. This Cl, it's not combined with any other elements. Notice it's combined with itself, but it's not with another element. So the oxidation number, we call that free. The oxidation number is 0. Free elements. Sometimes they talk about ions, where they actually give you just a single ion. If they said you have zinc 2+, the difference between charge and oxidation number, for your purposes, it's the same thing. But in chemistry, the difference is a charge has the number before the charge, so 2+. The oxidation number has the charge first. So if this is 2+, the oxidation number is +2. So if it's a monoatomic ion, monoatomic, one atom, ion, the charge is equal to the oxidation number is equal to the charge. The rest of the rules that I'm going to teach you refer to it when atoms are combined. Atoms are within compounds. So the first two we talked about when they're by themselves, when you see them by themselves in a reaction. But you also have to know what happens when they're combined. So now I'm going to talk about when they're combined. The first thing I need to talk about is anything in group 1 on the periodic table. Anything in group 1 on the periodic table has a charge, an oxidation state, of +1. Sodium in this compound, since it's in group 1 and it's in a compound, has an oxidation number of +1. Anything in group 2 is always +2 in a compound. So you need to know group 1 is +1, anything in group 2 is +2. Another rule you need to understand is oxygen. Oxygen is usually -2. Oxygen's -2 almost always. The only exception is when it's combined with fluorine. And the reasons probably won't even ask you about that, but you just need to know oxygen's -2 unless it's combined with fluorine. Another rule, fluorine. Fluorine is always -1. Fluorine is always -1. And the halogens, which you know are group 17 on the periodic table, are also usually -1. When they're the most electronegative, now you just go to table S and look for electronegativity, but when you just have a single element and a halogen, if the halogen's more electronegative, then it's also -1. So in other words, when the halogen, any halogen is combined with just a metal, it's -1. So fluorine's -1 always, and the halogens are usually -1 and always -1 with a metal. Another rule, hydrogen. Hydrogen is almost always +1. The only time hydrogen is not +1 is when it's combined with a metal. And when it's combined with a metal, it's -1. So hydrogen is +1, except when it's combined with a metal, and then that's called a metal hydride, and then it's -1. And the next rule I'm going to teach you is the most important rule you could possibly learn about oxidation number. The rule is the sum of the oxidation numbers in a compound, the sum of the oxidation numbers equals 0. How does that apply? Well, in order to do a problem with that, you have to understand all the other rules. So I'm going to show you how to do a problem with that. Let's say we have H2SO4, sulfuric acid, in case you didn't know. H2SO4, the first thing you need to know is go over the rules. Well, it's a compound, so none of them are 0. Do we know a rule for hydrogen? Oh yeah, hydrogen's +1. Oh wait, unless it's combined with a metal. Oh no, it's not combined with a metal. So hydrogen's +1. Sulfur. What's the rule for sulfur? Why can't I think of the rule for sulfur? The reason is there is no rule for sulfur. Sulfur is not one of those rules I taught you, so you're going to actually have to figure it out. So we're going to leave it blank for now. Oxygen. Oxygen, what's oxygen's rule? Well, let's see. Oxygen is usually -2 unless it's with fluorine. Well, it's not with fluorine, so it's -2. Now remember what I said. The rule is the sum of the oxidation numbers must equal 0. Regents tutor method for answering these questions is putting a T diagram underneath and separating the positively charged oxidation numbers and the negative oxidation numbers. Because remember, the sum has to equal 0. So that means the total positives have to equal the total negatives. How do I do that? Well, there's 2 hydrogens. Each hydrogen has an oxidation number of +1. So it's a total of +2. Sulfur, we don't know. Oxygen, there are 4 oxygens. Each oxygen is -2. 4 times -2 is -8. Now what are we missing? Remember, we need the negatives to equal the positives. We have 8 negatives and only 2 positives. How many more positives do we need? Oh, that's easy. 6. We need 6 more positives. So what's the oxidation number of sulfur? Since there's only 1 sulfur there, sulfur's oxidation number is +6. So now you know how to figure out oxidation numbers even when there's no rule necessarily that applies to that given element. And there are a lot of problems like this on the Regents which means there's a lot of practice problems for you guys and girls to figure out and solve. The next rule is that the oxidation number for polyatomic ions. Now remember polyatomic ions, and you can look up the concept on table E if you want. Polyatomic ions represent when substances are bonded together. But remember what we talked about before. When compounds are bonded together, the oxidation number total is 0. But in polyatomic ions, the oxidation number is equal to the charge. So for example, if we're looking at PO4, PO4's oxidation number is -3. And that's just the rule there. Now, there are practice problems. I'm going to do one problem with you just to figure out a little bit more about oxidation numbers. So let's say I wanted to do K2 Cr2 O7. It's a little similar to the one we did before, but it's also a little different. Well, what's the rule for K? Well, K is in group 1, so it's +1. Rule for chromium? There is no rule. We don't know. Oxygen, -2 unless it's with fluorine, and it's not with fluorine. Regents-Tudor method, draw the T. 2 times +1 is +2. 7 times -2 is -14. We need positives to equal negatives. We need +12 here. But there are 2 chromiums. Since there are 2 chromiums, this is +6 to equal 12. Because we want the total to be 12, so each chromium has an oxidation number of +6. And that's how you assign oxidation numbers. And you need to understand that before we move on to the next part of this lesson. So make sure that's clear. If it's not, pause this and go over questions on assigning oxidation numbers. Okay. Next thing we need to talk about are redox reactions. Now, a redox reaction, like we talked about in the beginning, represents reduction and oxidation occurring. Redox reaction, there's a loss of electrons, oxidation, and a gain of electrons. The most common type of redox reaction is a single replacement reaction. And if you need to know what single replacement reactions are, go to your concept on single replacement reactions. But the reason why single replacement reactions often result in oxidation redox reactions is because there's always an element on one side that's alone and then a compound on the other side, which means it has 0 oxidation state on one side and then a non-zero, which means it changed, either gained or lost electrons. So single replacement reactions, some synthesis, some decomposition, but it can never be double replacement reaction. So if they ever say on the regions, which of the following represents a redox reaction, it's usually the single replacement. It may be the synthesis, may be decomposition. It will never be double replacement. But the way you find out is you could actually write the oxidation numbers for every single substance in that formula and see if there's a change in oxidation. And we're going to do that now. We're going to talk about, let's say we have a redox reaction. The redox reaction we're going to talk about right now is zinc plus chromium yields chromium plus zinc. Now in this case, we don't have to figure out the oxidation numbers because they gave them to us. This is alone, so we know this has an oxidation number of 0. And this is alone, so it's 0. And these are equal to their charge. Now we have to figure out which one's oxidized and which one's reduced. But remember the rule. Oxidation is losing electrons, Leo. If it's losing electrons, the number is increasing. The oxidation number is increasing. Zinc goes from 0 to 2+. Zinc, therefore, lost 2 electrons. Therefore, zinc is oxidized. Copper went from 3+, it actually reduced its oxidation number. So we say it gained negatives. It gained 3 electrons. So chromium 3+ is reduced. If they said on the regions, which species is oxidized? You say zinc. If they said which species is reduced, you can't say chromium. Because chromium is this substance. You would have to say the chromium 3 plus ion. So zinc is oxidized, the chromium 3 plus ion is reduced. The next part of understanding a redox reaction is understanding half reactions, which are half the reaction. Well, if the whole reaction is oxidation plus reduction, then half the reaction is just the oxidation or just the reduction. And we have to be able to designate half reactions. So I'm just going to erase this for now, just to save more space. But we remember who is oxidized and who is reduced. And you have to be able to write the oxidation and reduction half reactions. Let's do the reduction one first, because that's a little easier. For the reduction half reaction, we know it started as chromium 3 plus. So for the reduction half reaction, and I call it RXN because that's reaction. For the reduction half reaction, we're going to start with chromium 3 plus. And what happened? It gained 3 electrons. So we have to add 3 electrons. Chromium 3 plus gained 3 electrons to produce chromium 0, the chromium atom. Remember, atoms are neutral, ions are charged. Refer to that. You can go to the concept on atom and ions if you're still confused. But this is the atom, this is the ion. That is the half reaction for reduction. Things you need to know about that? The electrons are always on the left side for reduction because you're adding them to the substance you start with. But it's a little more confusing for oxidation. Let's do the oxidation half reaction. Well, you know how to start it. It starts with zinc. And I'm just doing the half reaction for this equation. Each equation has their own half reactions. So zinc starts at 0. Did it gain electrons? No, it lost electrons. So you'd want to write minus 2 electrons here. But in chemistry, we don't write minuses. So we can't write plus 2 electrons here. And we can't write minus, so we have to do it to the other side. Zinc produces Zn2 plus, and it also produces 2 electrons. So the confusing thing is, oxidation is losing electrons, but you have to write plus 2 electrons here. But it's okay because you're doing it to the right side. When you're doing it to the right side, that's when you know it's oxidation. Because it's like the electrons are being released. You're given off. So for oxidation half reactions, the electrons are on the right side. For reduction half reactions, it's on the left side because you're gaining it. And one thing you have to keep in mind is redox reactions show conservation of mass and charge, which means the same number of atoms have to be on each side. Chromium, there's 1 here. Chromium, there's 1 here. That's fine. Mass is conserved. Zinc, there's 1 here. Zinc, there's 1 here. Okay, mass is conserved. How about charge? What's the total charge on this side? Well, there's 3 positives and then 3 negatives. Total of 0. What's the charge on this side? 0. Conservation of charge. What's the charge on this side? 0. 2 plus 2 electrons, also 0. So this shows conservation of charge. Sometimes they ask you to balance the half reactions. One thing you have to remember is if one substance loses an electron and another substance gains an electron, well, if one substance loses 2 electrons, how can one gain 3? They have to be equal. So in order to balance this, you have to make the electrons in the problem equal. So this reaction is actually not balanced, and we're now going to balance it. And the way we do it is we just make the electrons equal. Can I multiply one of these equations by a number that will make them equal? Well, here's 3. Can I multiply this equation to make these electrons 3? No. So I have to multiply both. Can I multiply a number to make these both 4? Nope. How about 5? Nope. How about 6? Yeah. I can multiply this reaction by 2 and this reaction by 3. Now I distribute this out, 2 chromium, 6 electrons, and 2 chromiums there. So let me put them there. 2 chromiums, 6 electrons I don't need to write, and 2 chromiums. That's halfway done. How about the zincs? 3 zincs, 3 zincs here, 6 electrons. Oh, now the electrons are equal. This is my full balanced equation representing the oxidation and reduction. So that's a complete balanced equation, just making sure that the numbers are equal. It's very important that you understand, when we talk about oxidation and reduction, how to figure out what's oxidized and what is reduced. And I'm going to give you one more problem, because I want to just show you one more thing about oxidation and reduction in terms of how the problems go. Let's say I have magnesium plus copper sulfate produces magnesium sulfate and copper. Now remember, single replacement reaction. This is a redox reaction. The first thing I do is I write the oxidation numbers. So magnesium is 0. That's easy because it's alone. Copper is 0. The sulfate, polyatomic ion, will never change its oxidation state because the charge of sulfate will always be -2. So I could just take this whole sulfate and just make it -2 because I know that will not be involved in the oxidation reduction. Magnesium we know is in group 2, so that's +2. How do I know what copper is? Well, if the sulfate ion is -2, how many positive charges do I need? +2. So the copper is +2. And then I want to figure out which is oxidized and reduced, and I'll write the half reactions. And I'll do this one a little quicker because now we have a little more information. Magnesium goes from 0 to 2+. It's oxidized. So how do I write the oxidation? Magnesium, remember the electrons are on the right. Magnesium 2+ plus 2 electrons. And that's my oxidation half reaction. And for my reduction half reaction, copper 2+ plus 2 electrons gives you copper 0. And that's my reduction. Do I have to balance these? No, because the electrons are equal. So this is already done. It's very important that you know how to find which substance is oxidized and which substance is reduced. And that will be more important as we go on in this lesson. So it's really important that you understand oxidation and reduction. Now, one thing you also need to keep in mind is that agents are opposite. And it's just very simple. If the substance is oxidized, then it's called the reducing agent. If a substance is reduced, then it's called the oxidizing agent. It's just the opposites. The next thing I have to talk about is an electrochemical cell. An electrochemical cell is a reaction in which it uses reduction and oxidation and there's an electric current going through. That's what an electrochemical cell is. Now there are two types of electrochemical cells. There are voltaic cells and electrolytic. Now they both have an electric current, but in a voltaic cell, the electric current is produced by itself, whereas in an electrolytic cell, it's produced not by itself. It's actually, you force a redox reaction to occur to produce an electric current. So, when you're doing voltaic cells and electrochemical cells, when you're doing electrochemical cells, the first cell I want to talk about is a voltaic cell. And if you look to my left on the slide screen, you'll see, and we'll talk about voltaic cells. In a voltaic cell, you always have two beakers. The two beakers in a voltaic cell contain a solution. Inside the solution are electrodes, which are just metal plates. This represents a copper electrode. This is a copper electrode. And it could be any electrode. It could be any metal. So you have two electrodes, one in each beaker. Connecting the two beakers, connecting the two metal plates, or the two electrodes, is a metal wire. The metal wire, you'll see the function later, but it's connecting the metal wire. And the switch is there to complete that circuit. So the metal wire is connected to the two electrodes, and the switch is closed, which means things can go through from one electrode to the other. The other thing that's contained in a voltaic cell is a salt bridge. Now, a salt bridge is also very important, and you see that connects the two beakers. The first thing I want to talk about is the salt bridge. The Regents loves to ask questions on the salt bridge. With the salt bridge, you need to understand what it does, and it does one thing. It allows ions to flow from one beaker to the next. And you can see in the slide, the ions are moving from one beaker to the next through the salt bridge. Don't confuse the salt bridge with anything else. It's not electrons that are flowing through the salt bridge. It's the ions that are flowing through the salt bridge. The next thing I need to talk about is the metal wire. Notice the metal wire is connecting the two electrodes. The two electrodes are connected by the metal wire. What you need to know about the metal wire is it allows the flow of electrons. Electrons flow through the metal wire from one electrode to the other. It can go either way when you don't know the metals. There is a set direction it takes, but for right now, since you don't know the metals, it can go either way. And see what would happen if the switch was closed? If the switch was open, the electrons wouldn't be able to go through. They'd be stopped by the open switch. So when we close the switch, they go right through. Okay. Metal wire and salt bridge you need to understand. Let's talk about specific metals for our voltaic cell. Let's talk about, it could be any metals, but let's say we're using zinc and copper. Zinc's on my left, copper's on the right. Okay. The zinc and the copper are the two electrodes. Now you have to figure out which electrode represents oxidation and which represents reduction. And before I go over that, you need to understand that the electrodes are just metal pieces, which are made up of many metal atoms. They're not ions. The ions are in the solution. The metal is made up of metal atoms. So the zinc electrode is made up of zinc atoms. In the solution, there are zinc ions. The copper is made up of copper atoms, and in the solution, there are copper ions. The first way to tell whether or not a substance which is reduced or oxidized is using Table J. Table J, over here, shows the activity series of certain metals. Now, we remember from the periodic table lesson, and if you don't, go back over and listen to it, but metals lose electrons. What do metals want to do? Again, they want to lose electrons. So Table J shows how active they are. Which metal do you think is going to be able to lose electrons more easily? The metal that's more active or the metal that's least active? Well, the metal that's more active will do what it wants to do, and it wants to lose electrons. Now, you should be thinking, wait a minute, lose electrons? Oh, that's oxidation, because Leo goes Gur. So what that means is the most active metals, highest up, will actually be oxidized. So when you're talking about zinc and copper, you see on the slide screen, zinc is higher than copper. Zinc's more active than copper. Zinc's going to do more of what metals want to do. Zinc's going to be oxidized. So in general, any metal that's higher up than the other metal will be oxidized. So you will notice that zinc is higher, so therefore zinc is oxidized, and copper is the site of reduction. And you'll see what I mean in a second. The other way you could do to find out which is oxidized or reduced is you do this simple equation. If I gave you an equation, zinc plus copper 2 plus yields copper plus zinc 2 plus, and you can see on the screen, well, the zinc loses 2 electrons to become Zn2 plus. The copper ion, the copper 2 plus, gains 2 electrons. Therefore, again, zinc is oxidized and the copper ion is reduced. Notice it's not the copper atom. It's not the Cu that's reduced. It's the copper ion. The next thing you need to know is, well, before I go on, you need to see that the zinc electrode is the site of oxidation, and the copper electrode is the site of reduction. Now, you see a red cat and an ox. Why do you see a red cat and an ox? You see a red cat and an ox because you need to know which electrode is named after reduction and which electrode is named after oxidation. the two electrodes could be called anode and cathode. Red cat means reduction occurs at the cathode. Anox is the anode, is oxidation. So in this case, since zinc is oxidized, zinc is the anode. In this reaction, since copper is the site of reduction, copper, red cat, the reduction occurs at the copper electrode, copper is the cathode. Okay, so you understand the copper, you understand the cathode and the anode because of red cat and an ox. And it's very important that you understand that. The last thing you need to know about a voltaic cell is how the electrons flow. And you just need to understand that electrons always flow from the anode to the cathode. And it makes sense, right? The cathode is gaining electrons. The anode is losing electrons. So the electrons leave the anode and enter the cathode. Because the cathode gains electrons, anode loses electrons. So it's really important you understand what an anode or cathode is, because then it will help you know the direction flow. So in this equation, the electrons, as you can see, will flow from zinc electrode to copper electrode. And this is a full voltaic cell flowing through. And that's the voltaic cell. Okay, good. The next thing we need to talk about is electrolysis. Electrolysis, or an electrolytic cell, remember electrochemical cells can either be voltaic or electrolytic. Both produce redox reactions and both produce an electric current, but only voltaic cell produces it by itself, spontaneously. An electrolytic cell is when the redox reaction is not spontaneous, where you actually have to add electricity to cause a reaction. And electrolysis, since you're doing it, one example of electrolysis is when you're electroplating a substance. So let's say you had a copper spoon and you wanted to plate it with silver. You would set up this machine where you'd have a silver electrode and then a copper spoon, and you'd actually cause the silver to electroplate onto the copper spoon. And the things you need to know about electrolysis, same rules, red cat and an ox. Reduction occurs at the cathode, anode is oxidation. Also need to know, in dealing with that, is that the object being plated, in this case the spoon, is the cathode. The object that the material's plated to, right? So you're plating silver onto copper. The material that's actually being plated is the silver, that's the anode. So the object being plated is always the cathode, and you need to understand that. And the same deal goes, the electrons always flow from the anode to the cathode. So if you understand that electrons always flow from anode to cathode, you'll have no problems. And that's voltaic cells and electrolytic cells. Now I just want to do a quick comparison of the two. First, let's talk about the similarities between a voltaic cell and an electrolytic cell. The similarities is they both use redox reactions. They both have oxidation and reduction, so they have a transfer of electrons. They both have the red cat and an ox, meaning the reduction occurs at the cathode and oxidation occurs at the anode. And the electrons always flow from anode to cathode in both. But there are very specific differences. The first one is a voltaic cell is spontaneous. Voltaic cell happens on its own. An electrolytic cell will not happen on its own. So you actually have to plug it in to cause electricity or electrons to flow in to cause it to happen. Voltaic is spontaneous, means it happens on its own. Electrolytic is non-spontaneous, means it can happen on its own. Voltaic cell produces its own electric current. Electrolytic cell requires the use of an outside electric current. A voltaic cell, very important to understand about a voltaic cell, is it converts chemical energy, the energy in the bonds, and you can click on the concept of chemical bond energy to see chemical bond energy, but it converts the chemical bond energy to electrical energy. That's why it produces an electric current, because that chemical bond energy is just converted to electrical energy. And in an electrolytic cell, it's the opposite. It doesn't produce its own electricity. It needs electricity, so it takes the electrical energy that's produced, that's supplied to it, and converts it into chemical energy. So a voltaic cell goes from chemical energy to electrical energy to produce an electric current, whereas an electrolytic cell requires an electric current and goes from electrical energy to make bonds or to make a substance into chemical bond energy. So I hope you learned a lot about redox and electrochemistry. This is a very complicated unit. Students tend to have a lot of trouble with this. So I expect you to go over the lesson again. I expect you to go over every question on redox and electrochemistry, every single question relating to this lesson. And even if you think you know the answer, I want you to listen to the video explanation. And if you still have questions, remember, we're there for you at Regents Tutor. Go to the chat, look at the review sheet, use all the resources you have available to you. I hope you learned a lot.